To the class. We are going to continue with the lesson P block element group 13 and 14 with the question answer session that we were doing. The first question today is in this on the screen, and the question is to explain why the elements of group 13 are expected to form covalent bonds in class 3 oxidation state. Now, group 13, the general electronic configuration is SN1, NS1 and NS2, NP1. Total of 3 valence electrons are present in the valence shell. Now, to produce class 3 oxidation state so that group 3 elements can form ionic bond in class 3 oxidation state, 3 valence electron present in the valence shell is required to be removed. Now, for this process, the total ionization energy, first ionization energy, second ionization energy, and the third ionization energy is required to be given to the elements. Now, the total amount of ionization energy becomes so excessively high, this entire process to remove 3 electrons is not feasible enough. As a result of this, group 3 elements form class 3 oxidation state by sharing 3 valence electron in a covalent bond formation instead of by losing 3 electrons to form ionic bonds. That's why group 3 elements form covalent bonds in class 3 oxidation state. That number 2 question, the next question, the compounds in which the elements of group 14 show an oxidation state of plus 4. The compounds in which the elements of group 14 show an oxidation state of plus 4 are expected to be covalent, whereas the compounds in which they show an oxidation state of plus 2 are expected to be ionic. This is the same logic that we had applied for the previous question. The general electronic configuration for the elements of group 14 is NS2NP2. There are total 4 valence electron present. Now, to form class 4 oxidation state, 4 valence electron is required to be removed from the valence shell, and thus total of 4 ionization energy is required, which is extremely high amount of energy, making this entire process energetically unfeasible. Whereas during the formation of plus 2 oxidation state, only 2 electron is going to be removed. 2 ionization energy is required. So this is quite feasible process. That's why when elements of group 14 form bonds, they form ionic bonds by losing 2 valence electron, but when they are forming plus 4 oxidation state, they form this by sharing their 4 valence electron instead of losing them. That's why they form the covalent bond in the plus 4 oxidation state and ionic bond, ionic compounds in plus 2 oxidation state. Now, the third question is explain why trihalides of boron act as Lewis acid. Let's try to construct the structure of trihalides of the boron. Now, the electronic configuration is 2s2 2p1. The ground state electronic configuration is in excited state, like in the case of BX3 trihalide of boron. one of the paired electron jumps to the one of the vacant 2p orbital, forming 3 unpaired electron. Then electron from 3 halide atom is shared with the unpaired electron of boron atom and thus form 3 boron halide covalent bonds, and thus forms the structure which have spt hybridization of boron. So the shape of the boron is trigonal bipyramidal, in which the vacant p orbital is perpendicular with the plane of the molecule. As a result, as there is a vacant p orbital, boron can accept electron, and also if we can calculate the numbers of electron in the bx3 molecule, there are 1, 2, 3, 4, 5, 6 numbers of total valence electron present in boron in bx3 molecule. But the octet is not filled. That's why boron in BX3 molecule is electron deficient in nature with a vacant p or p orbital. That's why boron in BX3 molecule can accept electron pair, and thus due to these two reasons act as a Lewis acid. The fourth question is, which one of BF3 and BI3 act as stronger Lewis acid? Now we know that BX3 boron in trihalides have vacant p orbital and the octet is not filled. That's why it can accept electron and act as Lewis acid. Now for BF3, fluorine atom has lone pair of electron. Now boron and fluorine have comparable size. That's why fluorine donates its electron and form a back bonding, thus reduces the electron deficiency of boron slight a bit. As there are 3 fluorine atoms, the back donation occurs from all the 3 fluorine atoms, resulting in reduction in the electrophilicity of the boron, reduction in the electron deficiency of the boron atom, which results in the Lewis acidity of the BF3 molecule. This is not as much feasible for BCl3 molecule. This back donation from the chlorine atom, which also comprises lone pair of electron, is not as much feasible as that of in the BF3 molecule, because chlorine has bulkier size compared to smaller boron atom, which results in this back donation quite difficult. That's why the electro deficiency of boron atom, which was reduced in BF3 due to back donation, is not as much present in the case of BCl3 molecule. So boron can act as Lewis acid much more compared to the BF3 molecule. That's why if we have to consider these reasons, the Lewis acidity of BF3 reduces compared to the BCl3. The fifth question is explain why tin 2 salts are used as reducing agent where lead 4 salts act as oxidizing agent. Now, group 14 elements, these tin 2 and lead 4 in their oxidation state. These are group 14 ions of group 14 elements. Lead resides in the sixth period, tin resides in the fifth period. Now, lead have high amount of inert pair effect which results in the inertness of the s orbital electron, ns orbital electron. As a result, as 4 valence electron is present in lead and 4 valence electron is required to remove to produce this 4 oxidation state of lead. So this oxidation state, lead in plus 4 oxidation state is unstable, whereas plus 2 oxidation state is stable. That's why any salt of lead in which lead is in plus 4 oxidation state tend to accept electron to produce lead in plus 2 oxidation state, resulting in oxidizing other material. That's why lead salt in which lead is in plus 4 oxidation state act as a very good oxidizing agent. That is, whereas for tin 2 can lose more 2 electrons from the ns orbital to produce tin in plus 4 oxidation state, and thus can reduce other element easily and can act as a reducing agent. Now, the next question is explain why PbI4 does not exist. The reason is 2. Pb, lead is in plus 4 oxidation state, which is an unstable oxidation state. To stabilize, not only unstable, this is the highest oxidation state. To stabilize lead in plus 4 oxidation state, which is highest and unstable for lead, and very high electronegative ion like F4 should be, highest electronegative element like fluorine is required, fluorine or oxygen. But in here, we are seeing that iodine is there and they are forming Pi4. Now, lead is present in 4 oxidation state and I minus is there. Lead is a highly oxidizing agent and iodine is highly reducing in nature. As a result, lead oxidizes this iodine to produce the I2. Therefore, forming lead in the second oxidation state, plus 2 oxidation state. That's why PbI4 is extremely unstable, making it almost non-existing. The last question is CCl4 does not undergo hydrolysis while SiCl4 hydrolyzes readily. Why? And along with it, there is another question. Let's go to that question later. Let's do the first question first. Now, to answer this question, we have to look at the reaction of the hydrolysis of SiACl4. The chemical reaction of SiCl4, hydrolysis of SiCl4 is this. How this is forming? Water have oxygen with lone pair. The water attacks the silicon with its lone pair. Thus, one Cl is leaving with an hydrogen from water. So one HCl is leaving the reaction medium, forming this reaction, forming this compound. Now this step is repeated 3 times more, where 3 water molecule reacts, and as a result of the 3 HCl molecule is leaving, is removed from the reaction medium, forming this compound after this hydrolysis. This is not possible for CCl4 because in silicon there are vacant d orbital present. That's why in this reaction, lone pair of oxygen can low oxygen with lone pair can attack the silicon, and silicon can accommodate this entire mechanism, the accommodate the incoming electron pair. Carbon on the other hand do not have the vacant d orbital. In fact, the entire valence shell is filled in the field for carbon in CCl for molecule. That's why, as evident from the hydrolysis mechanism, CCl4 cannot hydrolyze, but SiCl4 can hydrolyze. Now let's look at the last question. The last question is, give Lewis acidity order of SiF4, SiCl4, SiBr4, SiI4. Now SiF4 Lewis acidity, SiF4 have Lewis acidity due to the vacant d orbital present. Hence can accept electron pairs. That's why it can act as Lewis acidity. But as fluorine have lone pair of electron, it can donate and thus form the back bonding. As a result of this back bonding between from this fluorine to silicon, the electron deficiency of silicon reduces, and as a result the acidity also Lewis acidity also reduces. Now this back bonding decreases with the increase in the size of the halide atom from fluorine to chlorine, chlorine to bromine, bromine to iodine, which results in the higher Lewis acidity order. That's why the acidity order will be less than Si SiF4 less than SiCl4 less than SiBr4 less than SiI4.